In order to create the warp for our demonstration loom, we will need about 1,440 individual strands of yarn wound evenly and under tension onto our warp beam. But our yarn comes as one long strand wound on cones. So in order to turn this into this in a way that doesn't end up in a big tangled mess, we will work in stages using a succession of machines that allow us to build up our warp a few ends at a time. The first step on this journey is the spooler. This aptly named machine is designed to wind yarn onto a spool, 32 ends at a time. Our spooler was made by the Davis and Furber Company and is stamped with the date of 1919. It also hadn't been run in about 40 years and needed a little TLC. Generally, the machine consists of two parts, the bobbin stand and the spooler apparatus itself. Bobbins of yarn are placed on spikes on the bobbin stand to hold them in place, and the yarn ends are threaded through the overhead hooks, through a couple of tension rollers, and then through a series of guides that move with traverse or back and forth motion. This motion reduces wear on the rollers and winds the yarn onto a wider area of the spool. The spool is driven by this drum. The drum is specifically designed to be 1 yard in circumference, allowing the operators to gauge how much yarn is wound on the spool through the measuring apparatus, which clocks the number of rotations of the drum. This machine also has a system for automatically stopping if the yarn breaks, and a bell that can be set on the measuring apparatus that will sound once a certain amount of yarn has been wound on. We are not really sure if this spooler was ever used at the Thomas K. Woolen Mill. To date, we haven't found any records giving its provenance, and much of the museum's equipment came from other mills in the area. Machinery records indicate that the Thomas K. Woolen Mill had a spooler as early as 1890, and upgraded to a high-speed Witten spooler in 1941. As you can see from this picture, the Witten machine is a lot bigger and appears to use a larger size bobbin, the kind that came off the new Witten spinning frames introduced to the mill that same year. Most machines at the Thomas K. Woolen Mill operated through water power. Long, spinning shafts driven by the turbines set in the mill race ran throughout the factory, and machines were driven by belts and pulleys attached to these shafts. Some conversion to electric motors took place when the mill was in operation, but the entire museum was electrified in the 1970s as part of a federal program intended to help train a new generation of textile workers. At least one of each type of machine at the museum was converted for use with an electric motor. The motor affixed to the spooler runs on 3-phase power. Unfortunately, the museum only has 3-phase outlets on the south side of the museum exhibit. So the first step for us was to move the machine closer to the power source and wire on a new plug. Its old plug had been repurposed sometime in the distant past. Power source ready, we did a dry run on the machine to test the motor and the parts. It seemed like a simple task, but it got complicated really quick. The spooler is designed with an automatic stop mechanism. Metal guides are balanced on top of the yarn. If the yarn is to break, the guide falls and sets off a reaction which stops the machine. To avoid triggering the automatic stop, we had to tie up the guides all the way up. The machine was ready to go, but there were still 2 very big problems that needed addressing that came to light during the dry run. Our spooler was designed to take bobbins directly from the spinning mule to wind onto the spool. The yarn we had to work with came on cones, which were quite wide and did not all fit on the platform of the bobbin stand. With a little creative thinking and help from our caboose work group, we were able to design and fabricate a new platform for the bobbin stand to hold 8 cones, and a brand new platform for the floor to hold an additional 24 cones that we needed. The dry run also quickly showcased another problem. With just 32 ends per spool, we were going to need a lot more spools. But the spare spools we had in storage were too wide to fit our machines, and many had flanges on the side that were too long. The spooler is designed to have the spool make direct contact with the drum to wind the yarn. With flanges too long, contact couldn't be made between the spool and the drum. Thankfully, the caboose crew were up to the task of modifying the spare spools to be able to fit the machine. The flange ends were removed, and the middle spoke cut down to size, and then the flanges were shaved to size, and everything was reassembled. Modifications complete, it was time to thread up the spooler. Truth be told, I was really dreading this part because it looked super complicated, but it took only about an hour to get everything all set up. We pulled the thread from the cones over the guide bars and hooks in the bobbin stand, making sure no threads were crossing. The threads were then pulled to the hooks on the spooler side and down through the slots of the first traverse motion guide and underneath the first tension roller. The top tension roller actually just lifts up. The rollers are moved by the motion of the thread and not by the machine. The threads are pulled up between the two tension rollers and over the top in an S-shaped pattern, and then underneath the auto stop guides and through the second traverse motion guide to the drum. Originally, the wooden spools were likely roughed up with a knife enough that the splinters would keep the fuzzy yarn in place. We weren't feeling super confident with the splinter method, so we hedged our bets a little with a bit of blue tape laid sticky side up on the drum. The spool is placed between two bearings and then lowered by means of a geared rack down until the central part of the spool makes contact with the drum. Weights are used on the top of the rack to keep the firm pressure between the spool and the drum, as that contact is what drives the winding motion, but also measures the yarn as it is wound. There is a belt shipper lever on the side of the machine that moves the belt from an idling pulley onto one that's keyed onto the main shaft. Because we don't have a variable speed motor, our operator controls the speed of the machine by slipping the belt onto that keyed pulley. The less the belt is on, the more slippage there is and the slower the machine will turn over. Everything was in place and ready to run. The first couple of runs, we had some broken threads. We decided to make this a two-person operation, one person running the belt shipper and the other watching for the broken threads. If the thread breaks, we just tied it back together and kept on rolling. Before we began operation, we placed metal pins and the gradations of the clock to the side of the machine. Each pin represents about 30 rotations of the drum, or 30 yards wound on, to the spool. We have been putting about 300 yards of yarn or 10 holes on the clock per spool. We did not have any original pins and started out just using pieces of tape stuck to the gear. But Chris salvaged some scrap metal for us, and the added benefit is that the pin will actually pull back a clapper for the bell and give us a noise when we hit our goal. When the bell sounds and we hit the desired length, the next step is to pull off the spool and carefully cut and tie the ends together to keep them from getting tangled. The spool is then taken over to the next machine in the process, the creel, which we'll get into much more in the next episode.
Things. Here's something that's kind of, oh no, it turns, okay. And it's part of this lever, so that's been shoved that way. So the machine's probably pulling it this way with this lever. For right now, though, it looks about right, so.
Yeah, no, I'll touch the adjustments at all.
Well, it's a starting point.
Yeah, absolutely.